factors or other factors that might be used to explain how the response variable changes, it takes on its value, multivariable function. So one can use regression analysis to actually approximate functions nicely. And one can also use regression analysis to uncover functional relationships and validate functional relationships amongst the variables. So let's set up the general linear model from a mathematical standpoint. Distribution of the response variable is modeled simply as a linear function of the independent variables. So the xi's, xi1 through xip, are the p explanatory variables that relate to the response variables possibly, and the beta 1, beta 2, beta I are the or beta p are the regression parameters, which with this linear relationship varies across the different end cases. So, okay, now how broad are the models? Well, the models really are very broad. This, first of all, polynomial approximation that's indicated here, corresponds essentially to, a truncated Taylor series approximation to a functional form. Finally, time series regressions, where the cases I, 1 through n, are really indexes of different time points, can be applied. And so the independent variable. All right, so let's go through what the steps are for fitting a regression model. First, one wants to propose a model in terms of what is the, we have to identify or be interested in a particular response variable. And critical here is specifying the scale, a collection of independent variables, which to include in the model. And it's important to think about how general this setup is. I mean, once we've set up the model in terms of identifying the response and explanatory variables and the assumptions underlying, we're going to go through several of those, and you'll see those. And least squares is the first one, but they're actually more general ones. In fact, the last section of this lecture on generalized MS. And then fourth, we need to check our assumptions. Now, it's very often the case that at this fourth step, where you're checking the assumptions that you've made, critical part of any modeling process, and then if necessary, modify the model and assumptions and repeat this process. And what I can tell you is that this, anyway, a slightly simpler or weaker condition is to use the Gauss. If we extend upon that, we can then consider normal linear regression models, which Will had just suggested. And in this case, we can extend upon that to consider generalized Gauss-Markov assumptions, where we maintain still the zero mean for the residuals, but the general, we might have a covariance matrix, which now, I'm sure it comes as no surprise that Gaussian distributions don't always fit everything, and so one needs to get clever with extending the models to other cases, and there are specifying the estimator criterion in two. So how do we judge what's a good estimate of the regression parameters? Well, we're going to cover least squares, maximum likelihood, robust methods, which are contamination resistant. And other methods exist that we will mention, but not get into really in the lectures, are Bayes methods and accommodating incomplete or missing. And let's see, in case analyses for checking assumptions, let me go through this. Basically, when you fit a regression model, you check assumptions by looking at the residuals, which are the basically estimates of the epsilons, the deviations of the dependent variable from their predictions. And what one wants to do is analyze these to determine whether our assumptions are appropriate. Okay, with the Gauss-Markov assumptions, you know, it would be, do these appear to have constant variance? Okay, so with that introduction to regression, linear regression, let's talk about ordinary least squares. Okay, the least squares criterion is for a given regression parameter beta, which is considered to be a column vector. So I'm taking the transpose of a row vector. The least squares criterion estimate, beta hat, minimizes this function. So in order to solve for this, we're going to use matrices. And so we're going to take the y vector, the vector of n values of the dependent variable or response variable, and x, the matrix of values of the independent variables. And it's important in this setup to keep straight that cases go by rows and columns go by values of the independent variable. Okay. Boy, this thing is ultra sensitive. Excuse me. Try to turn off the touchpad there. Okay. So we can now define our fitted value y hat to be equal to the matrix x times beta, and with solves the derivative of this criterion equaling 0. Now, that's in fact true, but who can tell me why that's true? Say again? Okay, so your name? Seth? Seth. Very good, Seth. Thanks, Seth. So if we want to find a minimum of Q, then that minimum will have, if it's a smooth function, beta by d beta j. Well, you just take the derivative of this sum, and so we're taking the sum of all these elements. And if you take the the derivative is a linear operator, so the derivative of a sum is the sum of the derivatives. So we take the summation out, and we take the derivative of each term. So we get 2 minus xij, then the thing in square brackets yi minus that. And what is that? Well, in matrix notation, if we let this sort of bold x sub square j denote the jth column of the independent variables, then this is minus 2, basically the jth column of x transpose times y minus x beta. So this jth equation for ordinary least squares has that representation in terms in matrix notation. Now, if we put that all together, we basically can define this derivative of Q with respect to the different regression parameters as basically the minus twice the jth column stacked times y minus x beta, which is simply minus 2x transpose y minus x beta. And this has to equal 0. And if we just simplify, taking out the 2, we get this set of equations must be satisfied by the ordinary least squares estimate beta. And that's called the normal equations in books on regression modeling. So let's consider how we solve that. Well, we can re-express that by multiplying through the x transpose on each of the terms. And then beta hat basically solves this equation. And if x transpose x inverse exists, we get beta hat is equal to x transpose x inverse x transpose y. So with matrix algebra, we can actually solve this. And matrix algebra is going to be very important to this lecture and other lectures. So if this stuff is, if you're a bit rusty on this, do brush. So now if beta hat doesn't have full rank, then our least squares estimate of beta might be non-unique. And in fact, it is the case that if you are really interested in just predicting values of a dependent variable, then having sort of non-unique least squares estimates isn't as much of a problem, because you still can get estimates out of that. But for now, we want to assume that there's full column rank in the independent variables. All right. Now, if we plug in the value of the solution, for the least squares estimate, we get fitted values for the response variable, which are simply the matrix x times beta hat. And this expression for the fitted values is basically x times x transpose x inverse x transpose y, which we can represent as h. Now the residuals are basically the difference between the response value and the fitted value. And this can be expressed as y minus y hat, or in minus h times y. And it turns out that in minus h is also a projection matrix. It is projecting the data onto the space orthogonal to the column space of x. And to show that that's true, if we consider the normal equations, which are x transpose y minus x beta hat equaling 0, that basically is x transpose epsilon hat equals 0. And so from the normal equations, we can see that what they mean is they mean that the residual vector epsilon hat is orthogonal to each of the columns of x. You take any column in x, multiply that by the residual vector, and you get 0 coming out. So that's a feature of the residuals as they relate to the independent variables. Okay. All right. So, so at this point, we've gone through really not talking about any statistical properties to specify the betas. All we've done is we've introduced the least squares criterion and said what value of the beta vector minimizes that least squares criterion. Let's turn to the Gauss-Markov theorem and start introducing some statistical properties, probability properties. So with our data y and x, yes, yes. That epsilon. Okay, let me go back to that. It's that x, the columns of x, and the column vector of the residual are orthogonal to each other. So when we have data y and x again, and now we're going to think of the observed data, little y1 through yn, is actually an observation of the random vector, capital Y, composed of random variables y1 to up to yn. And the expectation of this vector conditional on the values of the independent variables and the regression parameters given by x beta. So the dependent variable vector has expectation given by the product of the independent variables matrix times the regression parameters. And the covariance matrix of y given x and beta is sigma squared times the identity matrix, the n-dimensional identity matrix. So the identity matrix, has ones along the. All right. Now the Gauss-Markov theorem. This is a sort of a terrific result in linear models theory, and it's terrific in terms of sort of the mathematical content of it. I think it's. For a math class, it's really a nice theorem to introduce you to and sort of highlight the power of I guess, results that can arise from applying the theory. And so to set this theorem up, we want to think about trying to estimate some function of the regression parameters. And so, okay, our problem is, let's see. Actually, these notes are going to be distributed, so I'm going to sort of go through this very, very quickly and come back to it later if we have more time. But you basically, the argument for the proof here is you consider another linear estimate, which is also an unbiased estimate. So let's consider a competitor to the least squares value, and then look at the difference between that estimator and theta hat. And so that can be characterized as uses this orthogonality of f and d to evaluate the variance of theta tilde. And in this proof, the mathematical argument here is really something. I should put some asterisks a few lines here. This expression here is actually very important. We're basically looking at the decomposition of the variance to be the variance of b transpose y, which is the variance of the sum of these two random variables. So the page before basically defined d and f such that this is true. Now, when you consider the variance of a sum, it's not the sum of the variances. Variances of sums of random variables, you have to really keep track of the covariance terms. In this case, this argument shows that the covariance terms are in fact 0, and you get the result popping out. But that's really a, I don't know, in econometrics class, I'll talk about blue estimates of regression, or the blue property of least squares estimates. That's where that comes from. All right, so let's now consider generalizing from Gauss-Markov to allow for unequal variances and possibly correlated non-zero covariances between the components. And in this case, the regression model has the same linear setup. The only difference is the expectation of the residual vector is still 0, but the covariance matrix of the residual vector is sigma squared, a single parameter times, say, capital sigma. And we'll assume here that this capital sigma matrix is a known n by n positive definite matrix specifying relative variances and correlations between the observations. Okay. Well, in order to solve for regression estimates under these generalized Gauss-Markov assumptions, we can transform the data yx to y star equals sigma to the minus a half y, and x to x star, which is sigma to the minus a half x. And this model then becomes a model, a linear regression model in terms of y star and x star. We're basically multiplying this regression model by sigma to the minus a half across. And epsilon star actually has covariance matrix equal to sigma squared times the identity. So if we just take a linear transformation of the original data, we get a representation of the regression model that satisfies the original Gauss-Markov assumptions. And what we had to do was basically do a linear transformation that makes the response variables all have constant variance and be uncorrelated. So, so with that, we then have the least squares estimate of beta is the least squares, the ordinary least squares in terms of y star and x star. And so plugging that in, we basically have x star transpose x star inverse x star transpose y star. And if you multiply it through, that's how the formula changes. So, and so this formula characterizing the least squares estimate under this generalized set of assumptions sort of highlights what we're trying, or what you need to do to make the, to be able to apply that theorem. So with response values that have very large variances, you basically want to sort of discount those by the sigma inverse. Okay, the y conditioning on the values of the independent variables, the y's, the response variables are going to be independent over the index I. They're not going to be identically distributed because they have different means, mu I for the dependent variable yi, but they will have a constant variance. And what we can do is basically condition on x, beta, and sigma squared, and then represent this model in terms of the distribution of the epsilons. So if we're conditioning on x and beta, this x beta is a constant known. We've conditioned on it. And the remaining uncertainty is in the residual vector, which is assumed to be corresponding mean vector, and a covariance matrix given by the covariance matrix. In terms of independent and identically distributed values, the probability structure here is totally well defined. You know, anyone here who's taken the beginning probability class knows what the density function is for this multivariate normal distribution, because it's the product of the independent density functions for the independent components, because they're all independent random variables. So this multivariate normal random vector has, okay, here I'm just highlighting the, or defining the mu vector for the means of the n cases of the data. And the covariance matrix, sigma, is this diagonal matrix. And so basically sigma ij is equal to basically sigma squared times the Kronecker delta for the ijth element. Now, what we want to do is under the assumptions of, and so Chungbom introduced the moment generating function for individual random variables, for single variate random variables. For n variate random variables, we can define the moment generating function of the y vector to be the expectation of e to the t transpose y. So t is an argument of the moment generating function. It's another n vector. And it's equal to the expectation of e to the t1 y1 plus t2 y2 up to tn yn. So this is a very simple definition. Because of independence, the expectation of the products of, or this exponential sum is the product of the exponentials. And so this moment generating function is simply the product of the moment generating functions for y1 up through yn. And I don't know if it was in the first problem set or in the first lecture, but e to the ti mu I plus a half ti squared sigma squared was the moment generating function for a single univariate normal random variable with mean mu I and variance sigma squared. And so if we have n of these, we take their product, and the moment generating function for y is simply e to the t transpose mu plus a half t transpose sigma t. And so for this is its moment generating function. And this happens to be the distribution of y is a multivariate normal with mean mu and covariance matrix sigma. So a fact that we're going to use is that if we're working with the p vector of the betas, beta hats, and this is simply the definition of the moment generating function. If we plug in for basically what the functional form is for the ordinary least squares estimates and how they depend on the underlying y, then we basically, we have A equal to essentially the linear projection of y that gives us the least squares estimate. And then we can say that this moment generating function for beta hat is equal to the expectation of e to the t transpose y, where little t is a transpose tau. So, well, we know what this is. This is the moment generating function of of y, evaluated at the vector little t. And so we just need to plug in with little t that expression a transpose tau. So let's do that. And you do that, and it turns out to be e to t transpose mu plus that. And we go through a number of calculations. And at the end of the day, we get that the moment generating function is just e to the tau transpose beta plus a half tau transpose this matrix tau. And that is the moment generating function of a multivariate normal. So these few lines that you can go through after class basically solve for the moment generating function of beta hat. And because we can recognize this as the MGF of a multivariate normal, is essentially the conclusion of that previous analysis. The marginal distribution of each of the beta hats is given by beta hat by a univariate normal distribution with mean beta j and variance equal to the diagonal. Now, at this point, saying that is like an assertion, but one can actually prove that very easily given sort of this sequence of argument. And can anyone tell me why this is true? Express this as a product of an orthonormal matrix, Q, which is n by p, and an upper triangular matrix R. It turns out that any matrix, n by p matrix, can be expressed in this form. And we'll quickly show you how that can be accomplished. We can accomplish that by conducting a Graham-Schmidt orthonormalization of the independent variables matrix X. And let's see. So if we define R, the upper triangular matrix in the QR decomposition, to have basically zeros off the diagonal below and then possibly non-zero values along the diagonal and to the right, we're just going to solve for Q and R through this Graham-Schmidt process. So the first column of X is equal to the first column of Q times the first element, the top left corner of the matrix R. And if we take sort of the cross product of that vector with itself, then we get this expression for R11 squared. We can basically solve for R11 as the square root of this dot product. And Q1 is simply the first column of X divided by that square root. So this first element of the Q matrix and the first element R, this can be solved for right away. Then let's solve for the the second column of Q and the second column of the R matrix. Well, X2, the second column of the X matrix, is the first column of Q times R12 and plus the second column of Q times R22. And if we multiply this expression by Q1 transpose, then we basically get this expression for R12. So we actually have just solved for R12, and Q2 is solved for by the arguments given here. So basically, we sort of successively are orthogonalizing columns of X to the previous columns of X through this Gram-Schmidt process. And it basically can be repeated through all the columns. Now, with this QR decomposition, what we get is a really nice form for the least squares estimate. Basically, it simplifies to the inverse of R times Q transpose Y. And this basically means that you can solve for least squares estimates by calculating the QR decomposition, which is a very simple linear algebra operation, and then just do a couple of matrix products to get the, well, you do have to do a matrix inverse with R to get that out. And the covariance matrix of beta hat is equal to sigma squared X transpose X inverse. And in terms of the covariance matrix, what is implicit here, but you should make explicit in your study, is if you consider taking a matrix R inverse Q transpose times Y, the only thing that's random there is that Y vector. Okay, the covariance of a matrix times a random vector is that matrix times the covariance of the vector times the transpose of the matrix. So if you take a matrix transformation of a random vector, then the covariance of that transformation has that form. So that's where this covariance matrix is coming into play. And from the MGF, the moment generating function for the least squares estimate, this basically comes out of the moment generating function definition as well. And if we take X transpose X, plugging in the QR decomposition, only the R's play out, giving you that. Now, this also gives us a very nice form for the hat matrix, which is turns out to just be Q times Q transpose. So that's a very simple form. So now, with the distribution theory, this next section is going to actually prove what's really a fundamental result about normal linear regression models. And I'm going to go through this somewhat quickly, just so that we cover what the main ideas are of the theorems. But the details, I think, are very straightforward, and these course notes that will be posted online sort of go through the various steps of the analysis. But okay. So there's an important theorem here, which is for any matrix A, m by n, you consider transforming the random vector y by this matrix A. It is also a random normal vector. And its distribution is going to have a mean and covariance matrix given by mu z and sigma z, which have this simple expression in terms of the matrix A and the underlying means and covariances of y. Okay, earlier we actually applied this theorem with A corresponding to the matrix that generates the least squares estimates. So with A equal to x transpose x inverse, we actually previously went through the solution for what's the distribution of beta hat. And with any other matrix A, we can go through the same analysis and get the distribution. So, so if we do that here, well, we can actually prove this important theorem, which says that with least squares estimates of normal linear regression models, our least squares estimate beta hat and our residual vector epsilon hat are independent random variables. So when we construct these statistics, they are statistically independent of each other. And the distribution of beta hat is multivariate normal. The sum of the squared residuals is in fact a multiple of a chi-squared random variable. The sum of n squared residuals is in fact an n minus p chi-squared random variable scaled by sigma squared. And for each component j, if we take the difference between the least squares estimate beta hat j and beta j and divide through by this estimate of the standard deviation of that, then that will in fact have regression parameter estimates and t statistics for those estimates. Now, okay, in the course notes, there's a moderately long proof, but all the detail likelihood estimation. And in fitting models and statistics, maximum likelihood estimation comes up again and again. And with normal linear regression models, it turns out that ordinary least squares estimates, in fact, are maximum likelihood estimates. And what we want to do with in maximum likelihood is to maximize, or we want to define the likelihood density function. Basically, we have these independent random variables yi, whose product is the joint density. The likelihood function turns out to be basically a function of the least squares criterion. So if you fit models by least squares, you're consistent with doing something decent, at least applying the maximum likelihood principle, if you had a normal linear regression model. And it's useful to know when. We'll just talk a little bit about generalized M estimators. Those provide sort of a class of estimators that can be used for fitting robust